Here. Okay, so last class, at the end of 1.1, we talked about the lengths, and these were the formulas I gave you for the lengths, that if you had a vector in R2, that means two elements in it, that the length, and that's just the symbol for length, is the square root of a squared plus b squared, and R3 would be a squared plus b squared plus c squared, and so on. If it was bigger, you would just keep doing the same thing. Well, a squared plus b squared is actually called something else in linear algebra. So that's going to bring us to the next topic, which is the dot product. So length we did. Dot product. So you have to have a dot, whereas in our regular, say, calculus, if you were writing u times v as two real numbers multiplied together, you might just write uv together, and it's understood to be a multiplication. In linear algebra, you need to either have a dot, and then there's another kind of multiplication, which is a cross product. So there's two different types of multiplication. So you have to have the symbol. So the dot is important. So the dot product works like this. If u is a vector AB and v is CD, then the dot product is found by multiplying corresponding entries. So you would multiply A times C, and then you would add B times D. And notice I don't have a bracket around there because that is going to give you just a number, which we would call a scalar. Like scalar multiple, right? Remember we said a scalar was a real number? So it gives a number. So it doesn't give a vector. The cross product, which we're going to see later tonight, gives a vector as an answer, and the dot product gives a scalar. Okay, so it gives a number, and the number means something. We're going to see that in a minute. Or it gives some hints about things. So for R2, find the dot product So the example we're going to do, the instructions are find the dot product of the following sets. So we're going to do 3 different cases. 4 different cases. And so the 4 different scenarios that we could have. So we'll do 4 different examples. We're going to draw them and see what the dot product gives us according to what the graph looks like. Okay, so for the first one, we'll say U is 2, 3. And V is negative 1, 2. So the dot product, we would say U dot V. I usually write the vectors, but it's not needed if you can do it in your head. So 2 times negative 1 plus 3 times 2. So negative 2 plus 6 is 4. So this one gives us 4. So let's draw them. I don't know what side I just measured that on. Okay. Okay, so 2, 3, 1, 2, and up 3. So standard position means just using 0 as your starting point. So if we put the point 2, 3 in, that vector, so this is u, and v, -1 and up 2. Remember, don't draw it beyond the point because it has a length. So here's v, so they're not a line that you're connecting. Okay, so we'll just leave the picture and the answer for now until we see all 4 cases. Okay, and then you can tell me what the dot product means. So the dot product of this one was 4. B. So we're going to do the same thing 4 times. I'll write all 4 down and you can actually try. So 2, 3, V is -4, 1. Okay, so you can find the dot product and then we'll draw that. Okay, so 2 and up 3. And 1, 2, 3, 4, and up 1. Okay, did anyone get the dot product for this one? So 2 times -4 plus 3 times 1, -5. Okay. Any guesses so far? Yeah. Unless you took it before and you know the answer, you can still pretend you're guessing. Any guess so far what the dot product means according to the graph? You don't have to say your guess out loud. You can think your guess. We have 2 more cases. Okay, C. Okay, so 2, -1, and 1, 2. What was the dot product of this one? 0, yep. Any guesses yet? Can we see all 4 of them on the screen? Okay, so these are all the possibilities. So, with the exception of the last one, okay, the last one is an exception. And why is the last one an exception? Can you tell me? Without knowing even what it's an exception of? When I drew the graph, what is it? They're on the same line, right? They're what do we call them? Parallel. Right, so with the exception of a line being parallel, okay? So in R2, you should be able to notice that they're parallel. So if they're not parallel, the rule with the dot product is if the number is positive, the dot product's positive, it tells something about the angle between them. If the dot product is negative, it tells something about the angle between them. And if the dot product is 0, it tells something about the angle. So what is it telling us about the angles of these?
If it's 0, the angle is 90.
Right.
If it's positive, it's less than 90. If it's negative, it's greater than.
Right, so less than 90 degrees is called acute. Greater than 90, obtuse. This is a 90-degree angle. So, it can have negative or positive, because if they're parallel lines going the opposite direction, you'd actually end up with a negative. But, so parallel lines, you can't just, you have to say to yourself, okay, the dot product's 2, but are they parallel? Because that wouldn't tell you that it's an acute angle, right? Or it's negative. If they were in the opposite direction, you'd end up with negative 10 here, if they were the same numbers. Okay, so in general, the dot product tells you something about the angle, okay, as long as they're not right angle. And it does the same thing in R3. So in R3, we could do the same thing. It's harder to draw because when we draw them in 3D, you can't really tell by looking at them on a 2D surface whether they're a bigger angle or a smaller angle. It's sometimes hard to see that. So the length, I said this had something to do with the length, and that is that the length of a vector, also called the magnitude, is the square root of the dot product of the vector with itself for any vector size, for any vectors. Okay, so there's a formula we often see if we square both sides. The dot product of a vector with itself is equal to the length squared. And there's some homework questions that have that you need that fact to figure them out. Okay. Find the length of (3, 0, minus 4). So you can use this dot product way, or you can use the other. So the length is the square root of u dot u, which is 3 times 3, 0 times 0, and negative 4. So 9 plus 0 plus 16 is 5. Okay, so the length of this vector is 5, of whatever units these are in. Now, we have something that's called a unit vector. So, what's a unit vector? Unit means 1. So this is find a vector in the same direction as you, but has a length 1 instead of a length 5. Right? So let me show you how to draw in 3D, one way to draw. I'm not really going to ask you this, but sometimes it becomes useful, and maybe in a different course it will become useful. So let's draw the vector. Oops. This isn't a good one to show an example of drawing, so I will show you another example after this without a 0 in it, okay? So when we're drawing in if any of you are in engineering, you'll have to do this in other courses. So X, Y, Z, they go to the right. Okay, you can put your X here, but then it would have to be Y, Z. It has to go to the right, X, Y, Z. You could also put X up here, but this would be Y and Z. Okay, so the order that they're in has to be the same order. Okay, so this is your X, your Y, your Z. So we're going to go 3 on the X. So we go 3 in the X direction. This would be the negative X this way, negative Y, negative Z. We don't usually show it because once you get too many lines on there, it starts to look confusing. Okay, so we're going 3 in the X direction. This is saying how many in the Y direction? 0. So we stay here. We don't go anywhere from here. And then this is minus Z. So the positive Z direction is up, and the negative Z direction is down. What you do in normal graphs here is you find like 1 and 2 and then you go in between them. You can't do that here. So you actually go from this point where we're at, the 3, and you go in the direction that you want to go. You don't go back over here and count down 3. So you have to go down 3 from here. 1, 2, 3, sort of down. 1, 2, 3 down. And then, or 4, sorry, 4, because it was negative 4, and that would be our spot. Now we didn't move in the Y direction, so to see this, where it is, think of that as like a plane going straight down like a piece of paper. It's lying on this line. Right, can you see it? And that bottom corner is where we stop. So this is the point 3, 0, negative 4. And if we put it in standard position, then it's right along that sheet of paper and ends right here. Okay, so that little plane. I'll show you one that doesn't have a 0 in a few minutes. Okay, so that vector right there has a length 5. If we wanted a vector that has length 1, so unit vector means length 1, in that same direction, so it's parallel or lies on top of that, because we want it in the same direction, but we want it to only be a fifth. What would we do? I already told you the answer. I just said it. It has to be a fifth of the length. So what do you think we might do? We take U, a vector, and we divide it by the length, which is 5. So this looks like 1/5 of our vector, 3 over 5, 0 over 5, and minus 4 over 5. So this is a unit vector in the direction of U. Does that make sense? If we divide each of them by 5, because remember putting a scalar in front, like a 2, made it twice as long. So putting a fifth in front will take a fifth of it, right? So that's all we would do. Now, what if instead of a unit vector in the direction of U, we wanted to find a vector? Am I still on the sheet? Find a vector of length 3. Don't think too hard, because it's actually not very hard. This is a unit vector, so this has length 1. How would we make it length 3? Multiply that by 3. Yeah. Right? Now, if we didn't have the unit vector first to multiply it by 3, because this is length 1, if we multiply by 3, now it's going to have length 3. If we multiply it by 5, we're back to where we started, right? Because that's a fifth of it. The formula that they give looks like this. So you want a vector, k times the unit vector, to have a length of 3. Does that make sense? So we want to find k so that the length of k times u is 3. Right? That's what we're trying to do. And all we need to do is multiply by 3, of course. The vector we had, actually we'll keep this here. So if we didn't have that, this can be rewritten as k times the length of u. And if we want to find what k needs to be, we can divide both sides by the length of u, which we knew to be 5. Because we found it earlier, and that gives us the same thing. We divide it by 5 to make it a length 1, and then times by 3 to give it a length 3 that we wanted. So our vector of length 3 is 3/5 times u. What if I wanted it in the opposite direction? What do you think you do? Yeah, negative. So you would just do negative 3/5 times u. Just change all the signs. That was the length 3, I just changed the signs. Make sense? Okay, so then the angle between vectors. So here's the formula, and this is where I said you might need a calculator. And I put on the homework, so when I photocopy the pages for the homework, I just wrote on it, degrees is fine. The question in the book says, give it in radians and give it in degrees. So if you have your calculator in degrees, then just type it in, and right, degrees is fine, I don't care for that. Although there is another question on the homework that gives you the angle in radians, so all you would do is switch your calculator to radians and then do the question the same way. Okay? So just make sure your calculator's in the right, and like they give 2 radians, it's not things that we know, you know, by heart or anything, and you can just use your calculator for these. Okay, so we'll just do a couple examples using the formula. So find the angle Okay, so U is 2, -1, and V is 4/8. So we need the dot product and the length of each. So U dot V would be 2 times 4 plus a -1 times 8. Okay. What does that mean about them? They're perpendicular. And in linear algebra, of course, they don't actually say perpendicular, right? Although I don't mind if you do. Of course, there's another word for it. Orthogonal. Not orthogonal, which some people try to say when they read it, but it's orthogonal. But if you put perpendicular, I don't mind. But just so you know that in linear algebra, they don't say perpendicular, they say orthogonal. Right? And I don't mind if you say it wrong either. So, 90 degrees. We don't need to do the lengths of them because it's already, we know. So as soon as you get the dot product to 0, you can stop, you know the angle. We don't need the formula for that. Okay, B. Oh, that was a plus. Okay, so the dot product, U dot V. So √3 times 1 plus, so the dot product in R3, you just keep going, you multiply each corresponding entry, so 0 times 0 plus 1 times √3. So this will be √3 plus 0 plus √3 is 2 √3. Okay. Then we need, it's not 0, so we need to do the lengths of each. So the length of U is the square root of each of these squared and added together. So √3 squared plus 0 squared plus 1 squared. 3 plus 0 plus 1, which is 2. And this one's going to be the same, isn't it? It's also the same. It's the same 3 numbers, just in a different order. So then you would just fill it in. So cos theta equals, it's U dot V over the length of U times the length of V. So cos theta equals 2 √3 over 2 times 2. This is one that we know. Does anyone know it right off? I don't care if you do it on the calculator. If you're going to do it on the calculator, you would do theta is cos inverse of √3 over 2, making sure it's in degrees, and you would get your answer, which is, anyone know right off? Yeah, 30 degrees. Okay, and you can try that on your calculator to make sure you're plugging it in right, because you need the inverse cos and to get 30 degrees. Now, they don't always work out so nice. If we had two vectors that didn't work out, something like this won't work out probably to anything nice. I don't know what the answer is going to be, but if we do the dot product, also positive, so you know the angle is going to be acute, right, smaller than 90 degrees. Yeah, so this one won't work out nice. And then you would just put this in. So cos theta is the dot product over the length. 14 times 5. You might do it like that if you wanted to. And let's see. I don't even have it in degrees. Where do I switch that there? So on my calculator, I would hit the cos is in like orange, the cos inverse on top of the cos button. You probably can't see that there, but yeah, we probably won't be able to see it. But my cos button is here, and it's orange, so I have to hit second function in that to get the cos inverse. Can you see it? And then I would put it in a bracket. 1 divided by root 70, bracket. So 83.13, 83.114. Just make sure you have it in degrees if you're going to answer in degrees, right? Okay. And when I was doing the homework for this, actually section 1.3, I actually used my calculator a few times because the numbers in the book were like 18 times 47, and right? So on tests and things, I usually put smaller numbers, but you can bring your calculator if there's ever a number that's, I mean, it's just quicker than doing it out long. But there's nowhere really that it would be much benefit except just, you know, multiplying numbers. Questions about any of that? So the end of 1.2 is just some properties of dot product. Okay, so property 1, u dot v is equal to v dot u. And that's called, do you know what property that's called in math? When we can switch them around? I don't care if you remember the name of it, okay? But commutative, but you don't need to remember the name, okay? But if you ever hear that, that's what it means, that you can do it both ways. So it's commutative. The second property this is the distributive property, and it works for dot product as well, which is u dot v, sort of like you're multiplying it in, just like you would do normally, u dot v plus u dot w. So you can use the distributive property. You'll need this on the homework. So on the homework, there's a question, they give you this, and they give you a whole bunch of dot product answers. And in order to fill it in, you actually need to multiply it all out, and then you can fill in the little pieces. Okay, so that's a hint for one of the homework questions. Try to do the homework without looking at my answers, right? Try to figure them out first by looking in the notes. Don't jump right to the answer, because then you're not thinking enough about it, okay? If you can't get it after a long time, then look at my answer. But it's better to try to figure it out, even if you're stuck for a long time, looking back, looking in the notes, right? I just gave you a hint for one of them, that you have to multiply it out first. The third property, C is a scalar. So this property becomes useful later on, actually, not in this section so much, but later on this becomes useful. Like if you, for example, had a vector that was all divided by 5. So each number in it was like 2 over 5, 3 over 5, 47 over 5. What this is saying is you can take that 1 over 5 out to the front, do the dot product, and then put it back in later. You don't need to do it with the fractions in it. So what I mean is, for example, if you wanted to do the dot product of two vectors, I'll just make a simplified answer or example. Okay, I simplified and hard all at the same time. You could just do the dot product. Multiply 4 over 15 times 1/2, and that's fine, right? But what also works is if you take out, you notice I have a common denominator, 15, you can take 1 over 15 out of this, like that. You can take 1/2 out of this one, like that. What do you think you could do next? You can save those constants, those factors, till later. So we can actually rearrange this so that it's 1 over 15 times 1/2, and then do the dot product of these. So this is 1 over 30, and this would be 4 times 1 plus negative 12 times 3. I think by looking at this example, you can appreciate that that would help sometimes. Yeah, like if you're finding the length of this vector with 1 over 15s in it, you can actually take that out, do the length, and then put it back in. Right? So you can take constants out of vectors and do either the length or the dot product and then put them back in later. It makes things so much easier. Okay? So we'll see that. We'll use that later, not so much in this section, but it's a really, it's something good to know about the dot product. The next one I gave already is u dot u is equal to the length of u squared. Oops, thank you. U dot u is the length of u squared. And the last one, u dot v equals 0. Means the vectors are orthogonal or 90 degrees. So number 4 here is, for example, if you were given the length of u equals 3, and you were asked to find u dot u. So you need the length and you needed the dot product. So what would you do? Just square it, so the dot product would be 9, right? And that, you need that on the homework too. So u dot u is the length of u squared, which is 3 squared, so 9. Okay. So that's where you would use the properties. Yeah, for example, let me just put one example of that. Let's say we were given the length of u equals 2, the length of v is 3, and u dot v equals 1. And it said find this. So if we look at our properties here, so this is like our distributive property where you can multiply it in. So you can do the same thing as sort of like FOIL. If you had two brackets and you wanted to expand them, you could do that. So you would go 2u times u is 2u dot u, make sure you put the dot in there, and then multiply that by v, so minus, because there's a minus sign, 2u dot v, plus v dot u, minus, don't put squared, because there's no such thing as v squared, it's v dot v. Okay, because it's a dot product, you're doing a dot product of each. And the dot has to be in between them. You don't just put UV and like you normally would do. Now, given this information, can we figure this out? So we need u dot u, but we were given the length, right? And so u dot u is equal to the length of u squared. So u dot u would be equal to 2 squared, which is 4. U dot v was given, is 1. What about v dot u?
1.
Also 1, because it's commutative. V dot v? Right, the length of v squared, which is 3 squared, or 9. So our answer will be 8 minus 2 plus 1 minus 9, negative 2. What about this? This one. Say we had the length of u plus v. So normally if you were asked this and you knew the two vectors, you would add them together first and then you find the length. So we need to convert the length to a dot product so we can use the things we were given up here. Right? So what is the length as a dot product? The length is the square root of what? Whatever we want the length of. So u plus v dotted with u plus v. Does that make sense? right? Remember the length of u is the square root of u dot u. So now what? FOIL, multiply it out. So u dot u plus u dot v plus v dot u plus v dot v. And we found all these things up above, I believe. 4, 1, 1, 9. Okay, and one more question for this section. Okay, so I want to remind you something. Round brackets isn't a vector. You have to keep remembering that because I see on tests all the time people thinking these are vectors. Later when we have points and vectors in the same question, that all of a sudden people are thinking they're vectors when they're really points. So how do you know they're points? Well, it says vertices. Those are the corners, the corner points. And they have round brackets. And usually they're like this. Anyway, I write it like this. I'm not sure about the book, but you put A and then the bracket with not even an equal sign in between. That's a standard way to write that something's labeled A and is a point. So, but also it wouldn't be U, V, W. Those are all vectors. Okay, so A, B, C are usually points. Usually, because we use A, B, C later in a vector. So, of course, everything has an exception and is confusing. But these are points, not vectors. So we could draw these points, but basically if you've got 3 points and you connect them, that makes a triangle, right? So one other thing I want to point out about this question before we even do it is that I could word this question different, and you would approach it different. So right here, this says, show that the triangle is right-angled. So what do you know about the triangle before you start? It is a right-angled triangle. So when you on the test don't get it to work and you say this is not a right-angled triangle, you can assume that you're wrong. Do you understand what I'm saying? People do that all the time. Show that this is not continuous. Oh, but it is continuous, right? And then they go on to the next question. But I said it wasn't. So here I'm saying that it is a right-angled triangle, so watch for that. How could I word it that wouldn't tell you whether it was or not?
Give the angle.
Yeah, or determine whether the triangle is a right angle. Do you see the difference? Be careful of stuff like that. On every math test, in any course you ever take, if it tells you something about it, don't answer that it's not true. Okay? Because they're telling you it is. So this I'm telling you it's a right angle. So what do we know about it? That one of the angles is 90 degrees. And in vectors, what does that mean? So a dot product of two of the sides must be what? Must be 0. So how do we find the vector between points? That goes back to the last section, last class. If I give you points, how do you find a vector between them? yes,